All right, in this video, we're going to talk about section 2.3, dealing with continuity. And in this video, we're going to do some estimating of function values and limits using the graph of the function. Also, we'll be using the continuity properties of functions to determine whether a function is continuous. Now, as we've seen before, we have seen some graphs that have holes in them, and some have breaks, and some have other irregularities. So here we're going to be looking at each of these oddities in this section. So here we'll first give you the definition of continuity. And it's this: a function f is continuous at the point x equals c if, in number one, the limit as x approaches some constant c of f of x exists, also f of c exists, and the limit as x approaches some constant of f of x is equal to f of c. All three of these must be satisfied. And a function is continuous on the open interval a, b, if it is continuous at each point on that interval, okay? And as I mentioned before, all three of these conditions must pass, must be met. If one or more of these three conditions in the definition fails, then the function is discontinuous at x is equal to c, okay? So if any one of these fail, that means the function is discontinuous. So let's look at this example here. Here we're going to use the graph of the function to estimate the indicated function values and limits. So here we're going to complete parts A, B, C, D, and E. So in part A, we want to find the limit as x approaches 3 from the left of f of x. All right, so let's find 3 on this graph here. X is going to be the 3 right here. And we want the limit as x approaches 3 from the left. So we're coming in from the left of 3, which is this part right here. We're looking at the graph itself. So from the left of 3, the function value will be approaching 3. Actually, correction, it's approaching 2. So that means the limit as x approaches 3 from the left of f of x will be equal to 2. Okay. All right, part B is this: the limit as x approaches 3 from the right of the function f of x. So we're looking at 3 from the right of 3. Here it is right here, coming in this way from the right of 3. Notice that it's getting closer and closer to, in this case, -4. So the limit as x approaches 3 from the right, that would be -4. And then the limit as x approaches 3 of the function f of x. Well, we have to take a look at parts A and B. Here, the limit as x approaches 3 from the left must be the same as the limit as x approaches 3 from the right of the function. Here, from the left of 3, it's going to 2, but from the right of 3, the limit will be approaching -4. It's going to 2 different values here. So the limit as x approaches 3 itself of the function does not exist. And D and E represents does not exist. Okay. Now part D, evaluate f of 3. So we want to find out what the value of the function is when x is equal to 3. In this case, we do have a point here, and the y value that corresponds to x equaling to 3 would be 2. So f of 3 equals 2. And now part E is f continuous at x is equal to 3. Well, as follow, this continuity test up here. The limit of f of x, the limit as x approaches that constant of f of x, it should exist. In this case, it does not exist. So it violates that first rule or that first requirement. So in this case here, the function f of x is not continuous at x is equal to 3. Not continuous at x is equal to 3. Okay, on the next page is another example. Let's say I want to use a graph of the function to estimate the indicated function value limits. So here, completing parts A, B, C, D, and E, we've got the graph here. And I want to find the limit as x approaches -3 from the left. So in this case here, -3 is over here. And I want to go to the left of -3. So to the left of -3 would be coming in this direction. That's going to get closer and closer to some y value, which is in this case going to be 3. It won't reach 3, but from the left of -3, I should say, it gets closer and closer to 3. And then part B is the limit as x approaches -3 from the right. So here's -3, so I'm coming in from the right of 3. That's getting closer and closer to the y value of 3. And now the limit as x approaches -3 itself of the function f of x. Well, to the left of -3, it's getting closer to 3. To the right of -3 is getting closer to 3. So the limit of f of x as x approaches -3 would be 3. Notice the limit from the left is the same as the limit from the right of that function. Now let's evaluate f of 3. Let's take a look at that. And -3, here's a point right there at the y value of 5. So f of 3 is equal to 5. And then part B says if f is f continuous at x is equal to -3. Well, in this case, here, let's take a look at that continuity test on the first page. The limit as x approaches the constant of f of x does exist. F of c does exist, as you can see. But the problem is the limit as x approaches 3, -3 of that function is not the same as f of that constant. So here, it fails the continuity test. That means it is discontinuous, or we can just say not continuous at x equal -3. Okay. So that's how we apply that continuity test to determine whether a indicated function and its limits exist. All right, now here's some properties of continuity. And it's this: if two functions are continuous on the same interval, then their sum, difference, product, and quotient are continuous on the same interval, except for values of x that make the denominator 0. Okay, that makes sense. And the first theorem deals with the continuity properties of some specific functions. In part A, a constant function f of x equals to k, where k is a constant, is continuous for every x value. Meaning any x value that you assign to it, f of whatever that x value is, will always be that constant, regardless. Part B, for n, a positive integer f of x equals x to the n is continuous for all x. Okay. That's self-explanatory. X value raised to the power is going to be continuous for that function. Part C, a polynomial function is continuous for all x. That's because any x value that you assign to it, you will always get an f of x value for it. You're never going to get a 0 in the denominator. In fact, in a polynomial function, you won't have to have a 0 in the denominator or an x in the denominator. Part D, a rational function is continuous for all x, except those values that make the denominator 0. Okay. Just keep in mind, the rational function does have a variable in the denominator. Part E, for n an odd positive integer greater than 1, the nth root of the function f of x is continuous wherever f of x is continuous. And that's because for an odd index here, we can take odd roots of negative numbers and get a negative value for it. But for part F, for n being an even positive integer greater than 1, the nth root of the function f of x is continuous wherever f of x is continuous and non-negative. Because for an even root, we cannot take the even root of a negative number. That's undefined. But we can take the odd root of a negative number, like the cube root of -8. We can take the cube root of that, and that will be, of course, -2. But let's say we had the fourth root of 16. I mean, -16. That we can't. Here's some examples. Using that theorem and the general properties of continuities, determine where each function is continuous. So in part A, we got f of x is equal to x to the 4th plus 2x squared plus 1. Oops. That's just an expression. We need to write that as a function with f of x in front. Okay. If you look at that, you have a polynomial function. That means any x value that you assign to it, you're always going to get an f of x value for it. So that means here, its domain, I'm going to write this in interval notation. That's going to be negative infinity up to infinity, using parentheses. And if you're not familiar with interval notation, please check one of the videos back in chapter 1 that is related to where I did talk about interval notation. All right, part B. Here we got f of x is equal to x squared divided by x plus 1 times x minus 4. Now, in this case here, we do have a rational function because notice we have variables in the denominator. So that means we take what's in the denominator, set them equal to 0. So I'm going to take that x plus 1 times x minus 4, set that equal to 0. Then I'm going to set each binomial factor equal to 0. So x plus 1 times x minus 4 equal to 0 means this. X plus 1 is equal to 0, or x minus 4 is equal to 0. And then for each equation, we're going to solve for x. So for the x plus 1 is equal to 0, that means x is equal to -1. And then for the x minus 4 is equal to 0, that means x is equal to 4. So at -1 and 4, we're going to get a 0 in the denominator. All right. So now what I'm going to do here is, now if this helps, you can draw a number line like I'm about to do right now. Now here we got, let's see, 0 here, -1 on the left side, -1, and then 4 will be on the right side. So we know at -1, I'm going to draw an open circle. And at 4, I'm going to draw an open circle because those are the values of x that will give me zeros in the denominator. Any x value less than -1 would work. Any x value between -1 and 4 would work, and any x value greater than 4 would work. So the interval notation for this domain, let's see. The interval notation would be from -infinity up to -1, then from -1 to 4, and finally from 4 to infinity. That's the domain for the function f of x equal to x squared divided by x plus 1 times x plus 4. All right, now part C is f of x is equal to the square root of x minus 4. F of x equal to the square root of x minus 4. Now, in this case here, with a square root function, we need to find what values of x that will be positive, because I know it can't, well, positive or 0, because I can't take the square root of a negative number. So in this case here, I'll take that x minus 4, set that to be greater than or equal to 0. And to get x by itself, we'll add 4. That would mean that any x value greater than or equal to 4 would satisfy this square root function. And of course, if you need to, you can draw a number line. Since we're going to write this in interval notation, by the way. Now, we're going to draw a closed circle because of the equal to sign underneath it. Any x value greater than 4 would work. So the interval notation for that would be from 4 to infinity. All right. And part D looks like this. We got f of x is equal to the cube root of x cubed plus 1. Well, based on that theorem, we have an odd root. So for n being odd, positive integer greater than 1, the nth root of f of x will be continuous wherever f of x is continuous. Well, here, the f of x inside, that's continuous everywhere. Any x value that you assign to that, you will get an f of x value for that. So the cube root of that will have to be continuous everywhere. So that domain will be from -infinity to infinity. Okay. All right. Now here's some more practice on continuous, where functions are continuous. Like in example 4, determine whether the function f of x is equal to 8x minus 3 is continuous. F of x equals 8x minus 3. Well, That's a linear function which classifies as a polynomial function, which means that every x value that you assign to it, you will get an f of x value for it. So its domain in interval notation would be from negative infinity to infinity. Okay. All right, here's another example. Another rational function in this case here, determine whether the function where the function m of x equal to x plus 2 divided by x minus 2 times x minus 5 is continuous. Well, here we got a rational function where the variable is in the denominator. So we're going to take what's in the denominator, which is your x minus 2 times x minus 5. Set that to be equal to 0 because we want to find out what values of x that would give us a 0 in the denominator. So here in this case here, I'll set x minus 2 to be equal to 0 and x minus 5 to be equal to 0. Each equation will solve for x. So in this case here, for the x minus 2 is equal to 0. That means x is equal to 2. And then for the x minus 5 is equal to 0. That means x is equal to 5. Okay. So I would get a 0 in the denominator when x is equal to 2 or when x is equal to 5. And if this helps, it's not necessary. You can draw a number line to see what the interval notation would look like for this domain. Okay. It's 2, 5 is over here. We know at 2 and 5, we're going to get zeros in the denominator. So I'll use parentheses here. Any x value less than 2 will satisfy that rational function. Any x value in between 2 and 5 will satisfy that function. And any x value greater than 5 will satisfy that function. So the interval notation for that would be, for the domain, negative infinity to 2, or from 2 to 5, or from 5 to infinity. That would be the domain for that rational function. All right, next we'll look at another example, a couple of more of these. F of x equals to the square root of x minus 5. F of x equals to the square root of x minus 5. Well, it is a square root. It is an even root of a function. That means we need to find out what values of x will satisfy that function when I set x minus 5 to be greater than or equal to 0. Because I want this to be greater than or equal to 0. I can't take the square root of a negative number. So x minus 5 will be greater than or equal to 0. Then to solve for x, we'll add 5 to both sides, or to get x by itself, we'll add 5. So the x is greater than or equal to 5. Any x value greater than or equal to 5 will satisfy that square root function. So in this case here, if I draw a number line like this, let's see, 0 is here, 5 is here. 5 is going to be included, so we're going to use a bracket at 5. And any x value greater than or equal to 5 or greater than 5 will satisfy that function. So the domain here in interval notation would be 5 with the bracket to show that 5 is included onto infinity. And keep in mind, infinity always uses a bracket. Same holds true for negative infinity as well. All right, and example 7 is to determine whether the function f of x is equal to the cube root of 8 minus x is continuous. In this case here, if we have a odd root, that means if we're looking at here, we want to find out where it's continuous. It's continuous everywhere. That 8 minus x is continuous everywhere. Every x value that you assign to it, you're always going to get an f of x value for it. And the cube root will always be either positive or negative or 0. So in this case here, that domain is just simply going to be negative infinity onto infinity. Okay. All right, next we'll look at sign charts, where we're going to be solving inequalities using the continuity properties. So here we're going to be using sign charts. A tool for analyzing graphs of functions or for solving inequalities is the sign chart. We find where the function is 0 or undefined, then partition the number line into intervals as these points. We then test each interval to determine if the function is positive, which is above the x-axis, or negative, below the x-axis in those intervals. Okay. So for constructing sign charts, you're going to find all the numbers which are points of discontinuity where the denominator is 0, and points where the function is 0. That's where the numerator is 0, but the denominator is not. And then second, you're going to plot these partition numbers on a number line, dividing the line into intervals. Okay. So in this example that I have here, oh, by the way, there's 2 more steps. Select the test number for in each interval and determine if f of x is positive or negative there. And then you'll complete your sign chart by showing the sign of f of x on each open interval. Okay. So now in this example here, we're going to use the sign chart to solve the inequality x squared minus 4x minus 21 is less than 0. All right. So here we're going to express the solution in inequality notation and in interval notation. So for that x squared minus 4x minus 21 is less than 0, first of all, I'm going to treat this as x squared minus 4x minus 21 equal to 0 and find out what my x values are. Well, x squared minus 4x minus 21 can be factored into 2 binomials here. So I'm going to break x up as x, and factors of negative 21 that will give me negative 4x as a middle term will have to be minus 7 and plus 3. And that's because negative 7x and plus 3x does give me negative 4x, and negative 7 times the plus 3 will give me minus 21. So I have x plus 7 times x plus 3 is equal to 0. And then we set each binomial factor to be equal to 0. So in this case here, I'm going to have x minus 7 equal to 0, and x plus 3 is equal to 0. And then we're going to solve each equation for x. So for the x minus 7 equals 0, that would mean x is equal to 7. And for the x plus 3 is equal to 0, that would mean x is equal to negative 3. All right, so these are my 2 points where the function is 0, at 7 and at negative 3. So this is where I draw a sign chart. Okay. So here's my number line here. Here's 0, this negative 3 on the left, and 7 is on the right. Now that number line, those 2 values, we'll split this number line into three different intervals here. Here's one, the one on the left, the one in the middle, and the one on the right. So this interval is from negative infinity up to -3. This interval here will be from -3 to 7, and then this last one here from 7 to infinity. Now for each interval, I'm going to select a test point to determine whether the values in that interval will be positive or negative. So like for negative infinity up to -3, I would pick a test point like x equal -5. So I'm testing x is equal to -5. All right, now the original function is x squared minus 4x minus 21 is less than 0. This part right here, that's the f of x. So I'm going to write that down. That f of x is x to the x squared minus 4x minus 21. Now I'm going to substitute each x with -5. So f of -5 would be this, -5 squared minus 4 times -5 minus 21. Square the -5, you get 21. Minus 4 times that -5 would be plus 20 minus 21. And if you add 25 and 20, you'll get 45. 45 minus 21 will be 24. Notice that 24 ended up being positive. So for every x value from negative infinity to -3, I'm going to get positive f of x values. And now for the interval -3 to -3 to 7, a good test value for that would be x equals 0. So I'm going to test x is equal to 0. I might as well say f of -5 would be positive. Might as well say that. So now I'm going to find out what f of 0 is going to be. I want to determine if that's positive or negative. Well, f of 0 is just simply replacing each x with 0. So that's why it is a good test point to use, if at all possible. Because what's going to happen here is 0 squared is 0, minus 4 times 0 is 0, minus 21. This ends up being -21, which is, of course, negative. So f of 0 is negative. That means between -3 and 7, I will get negative f of x values. And then for 7 to infinity, this last interval, my test point for that would be x is equal to 8. So in this case here, I'm going to find out if it's positive at x is equal to 8 for this function. So here we just substitute each x with 8. So f of 8 would be 8 squared minus 4 times 0 minus 21. Not 4 times 0, 4 times 8. What I'm thinking about. Because I'm substituting each x with 8. Square this 8, you'll get 64. Minus 4 times 8 will be 32 minus 21. And in this case here, 64 minus 32 is 32. 32 minus 21 is 11. And 11 is a positive number. So in this case here, f of 8 is positive. So that means from 7 to infinity, it's going to be positive. Now, notice the inequality started off as less than 0. That means less than 0 has to be negative. So I need to select the interval that gave me negative values here. And in this case, this interval -3 to 7 is this interval that gave me negative values for f of x. So in interval notation, it will be negative 3, 7. And in inequality notation is this. I take negative 3, that's going to be less than some value of x, and that x value will be less than 7. So in this case here, that would be the solution in inequality notation and in interval notation. Okay, is that to select which interval gave me a negative value because of this inequality. Less than 0 means negative. Greater than 0 means positive. Okay. All right, let's look at this example here. Say we got x squared plus 5x divided by x minus 2 is greater than 0, and we want to use the sign chart to solve this inequality and write the solution in inequality notation and in interval notation. All right, in this case here, we're going to treat x squared plus 5x divided by x minus 2 greater than 0 as x squared plus 5x over x minus 2 to be equal to 0. But since we have a rational function in it, as we do in this case, what we need to do here is set the numerator of x squared plus 5x equal to 0 and the denominator x minus 2 is equal to 0. Okay, because if you have a rational function like this, you want to find the points where the function is 0, where the numerator is 0, but the denominator is not 0. So now we're going to solve each equation for x. Now for this x squared plus 5x equal to 0, we want to factor out the x. We want to find a common factor that's in x squared and 5x, and that's obviously going to be x. So here you got x squared divided by x, that's going to be x, plus 5x divided by x, which will be 5, equal to 0. And then I'm going to set each factor equal to 0. So I'm going to set x equal to 0 and x plus 5 equal to 0. Well, x equals 0, solve for x, but for the x plus 5 is equal to 0, x is equal to negative 5. And then for the x minus 2 is equal to 0, x will be equal to 2. Now that x equals 2, we know we're going to get a 0 in the denominator, so that has to be excluded. That's the value of x that gives us a 0 in the denominator. Now we can create our sign table for this inequality. Okay. Notice we got 1, 2, 3 values to deal with for x. See, there's 0, negative 5, and 2. So those 3 x values separate this number line into 4 intervals. There's 1, the 2 on the left, the 3rd, and then the 4th. This first one is from negative infinity to negative 5. The second one's from negative 5 to 0. The third one's from 0 to 2. And the last one from 2 to infinity. And now in this case here, we're going to select a test value or test number for each interval to determine whether the function is positive or negative in that interval. So like from negative infinity to negative 5, I'm going to pick x equal negative 6. So I'm going to test x is equal to negative 6. So that means here I'm just going to substitute, and I'm going to treat this as f of x. Let's see if I get enough room here. F of x is equal to x squared plus 5x divided by x minus 2. So I'm going to substitute each x with -6 in this function to see if it's positive or negative. So in this case here, -6 squared will be 36, plus 5 times -6 will be -30, over -6 minus 2 will be -8. 36 plus -30 is 6 over -8. And I can reduce it to -3/4, but here you can pretty much see that your function here will be negative. So that means here, from -infinity to -5, I'm going to have negative values for f of x. And then from -5 to 0, I will pick -1 as the test value. So I'm going to test x equal -1. And here's my function here. So I'm going to replace each x with -1. So f of -1 would be this. That'd be -1 squared plus 5 times -1 divided by, let's see, -1 minus 2. -1 squared would be +1 plus 5 times -1 would be -5 divided by -1 minus 2 would be -3. 1 plus a -5 would be -4 over -3. And that equals just a +4/3, but that's going to end up being positive anyway. So f of x would be positive on this interval. So from -5 to 0, I would get positive values for that function f of x. Now for the 0, 2, a test point for that would have to be x equal, let's say, 1. Then I'll find out whether f of x is positive or negative. So in this case here, f of 1 is going to be this 1 squared plus 5 times 1 divided by 1 minus 2. And in this case here, 1 squared will be 1 plus 5 times 1, which will be 5. 1 minus 2 would be -1. So I have 6 over -1 or -6, which is negative. So f of x from 0 to 2, I'm going to get negative values here. And then for 2 to infinity, let's try a test value like x is equal to, I chose 3. All right, in this case here, that would mean f of 3, when I substitute each x with 3 in f of x, I'm going to have 3 squared plus 5 times x, which is 3, divided by 3 minus 2. Well, 3 squared is 9. 5 times 3 is 15. 3 minus 2 is 1. 9 plus 15 is 24, divided by 1. Ends up being 24, but that's going to be positive. So that means f of x is positive on the interval 2 to infinity. Now, in this case here, I need to pay close attention to this inequality symbol. Greater than 0 means positive. So I need to pick the intervals that gave me a positive f of x value. And in this case here, this interval and that interval gave me a positive f of x value. Well, positive f of x values here. So the interval notation for that, move this over. The interval notation for that would be from -5 to 0, And since it's greater than, I have to use parentheses, not brackets, or 2 to infinity. And since 2 is not included, I have to use the bracket. Parentheses, since 2 is not included. So that's the interval notation. Now for the inequality notation, would be this. Since I got -5 to 0, that would mean -5 will be less than x and less than 0. Or from 2 to infinity means that any x value will have to be greater than 2. Okay. So that's how we write the interval notation and the inequality notation for that function, for this inequality here. All right, and that's how we use the sign charts to find out the intervals that will satisfy that given inequality. All right, so that does conclude this video on section 2.3, dealing with continuity. Please feel free to email me or reach out to me in any way if you have any questions about any of the material that's discussed in this video or any of the homework problems that are in my math lab.